All right, welcome back. We're starting lesson 6.3, starting our discussion about vectors, and their warm-up was to find the distance and the slope of the graph line segment. There's lots of discussion going on. It's great, lots of disagreement. So, two ways you could do this. You could use a distance formula. Here's our distance formula. If you don't remember this, come on, you guys have to do this like 8 billion times in geometry. You don't remember?
Happy times.
Oh, yeah, right.
I never looked at it.
So you basically just find the difference of your x coordinates.
And square it.
Square it. Find the difference of your y coordinates. Square it. Find that sum and then take the square root. Now, guys, you're really just. Don't you remember we did this? We proved the distance formula for this is just Python rearranged.
Yeah.
Question, Max?
Oh no, I was just making sure we have to do if we subtract the second x first, you have to subtract the second y first, correct? Like you can't do like switch them.
Right. Yes. Because you can't subtract in any order. So I just used distance formula and I just plugged in the 2 points. But really, you know, this distance right here, that's the difference of your x coordinates. That's just like your horizontal change there. Your difference of your y coordinates is this. And then to find the hypotenuse, square those, add them together, and then square root it. That's a distance formula. Okay, so that's what some of you guys did it that way too. So, yes, Max asked a good question. So if I start like with this point, 3, and I subtract this point in that order, then I have to keep it consistent because I'm subtracting. And I would do -2 minus 4. Okay, I did end up getting the square root of 61.
That's what I got.
Yeah, figured it out. We got that first time.
Yeah, because I don't know how that.
Definitely.
Okay. What did we get for the slope? -6 is what I got. Obviously we know this is going in the negative direction. It's going down from left to right. You could do you guys remember slope formula?
Y2 minus y1 over x2 minus x1.
Okay, so you guys remember that one. Good.
I know how to find the midpoint.
Tell me different.
Oh.
Tell me different.
Good. Or you can count, your rise over run. I like how Tyson pointed out, careful here that the boxes, you're counting up by half, so just be careful when you're counting, but you can also do rise over run and just stick on the direction. Me?
Yeah.
I just found this picture on Google.
Google did a terrible job.
No, it's not tricking, it's pay attention to details. That's what good mathematicians do.
We were just on spring break. Give me a second.
All right.
Long time you do one of those.
So since a lot of you aren't too familiar with vectors, we'll kind of just do like a little introduction to them today and look at some different forms. But basically, okay, if you guys kind of remember in geometry, we actually just got done doing this chapter. When you had to look at like scale models and like scales, like, on a map, like half an inch is equivalent to 36 miles an hour. Okay, so scalar is basically just like some quantity of like distance, or magnitude is like another word for distance. And a vector is something that has a magnitude, like a length, but also like gives us a direction. So let's just say I had like a brick right here, and if I moved it 2 feet to Ashton's desk, if I moved it 2 feet here, the scalar would be 2 feet, just like the magnitude, the distance that you moved it. But a vector would be, I moved it 2 feet to the right. Okay, it gives you both the distance, the magnitude, and the direction. All right. We do some application problems with this, but first we're gonna look at them like on a coordinate plane and just like introduce you to like the notation and like how we represent vectors and use them in more like a mathy context first. All right, so starting with just like a directed line segment is basically like one way we can represent a vector. So the directed line segments look similar to a line segment. You guys know a line segment has like 2 endpoints, right? But it has this arrow, and that is to show you what direction it's going, okay? Because that's one part of a vector, is it includes both magnitude and direction. So a common like example is like velocity. We do a lot with velocity in like calculus, where velocity is speed with direction, and velocity can be positive or negative. All right, so if you're, I don't know, having a negative velocity, that just tells you what direction you're traveling in. Okay, with scalars, we don't have that type of like direction context in them. All right, so basically some vocab. So your 2 points here, which are just designated by normal points, normal dots here. Wherever your arrow is pointed to, we call that like our terminal point. Terminal meaning like our end point. And then whatever point does not have the arrow, that's basically where our vector is starting. So we call that our initial point. And then we have this arrow to designate what direction. And then this terminal point here we call Q. So the notation of how I'd write out like this vector, and we'll look at a couple different ways you can notate this. But I would call this vector PQ, and you always want to start listing the initial point first. So in this case, P is my initial point. And then your terminal point second. Okay, here's another flashback to geometry for you geometry lovers. For lines, we use this notation. For rays, we use this notation. For segments, we use this notation. So for vectors, we do this notation where it's like this and then like half an arrow like that. That means vector. Well, directed line segment, but it's just a type of vector. We'll get there. Okay, so you have that bar to designate like the directed line segment. And then when you list them, you have to list it in the order of your initial point to your terminal point. Okay, I think that's all for vocab stuff. So let's draw some directed line segments here. So it says, sketch the directed line from P, so here's my initial point, to Q. Okay, and then we'll practice like naming that vector in a second. And then we're gonna do another one from R to S. Okay, so P, 1, 2. Q is 4, 4. Hopefully remember how to plot points. So the directed line segment would mean I would start here at P, from P to Q, and I would do an arrow like that. So this is technically, I guess, on a graph called like a directed line segment, and it's just one version of like a vector. So we'll build our way there. But that's technically a directed line segment from P to Q. So we could call that vector PQ, like that. All right, let's draw this one. This one starts at the origin, and the initial point is 3, 2. So this one's from R, S. So again, I would draw my arrow to show which direction from this point to this point, and we could notate this as vector RS. Okay, makes sense? That's just some of the notation stuff.
Is that all we gotta do?
For that one, yeah.
Oh my gosh, don't say
Okay,
that.
so as I was talking about, our vectors always include the magnitude and the direction. So when we're looking at the directed line segment specifically, with its initial point, P and Q, whatever that is, how we could calculate the magnitude or the length of that directed line segment is either by using the distance formula or by making a right triangle and using pi theta if you want to. But I could find the magnitude, which is just the length, the magnitude of these directed line segments, just like we did in the warm-up. Okay, so I personally like to use distance formula. I don't know about you guys. We'll write down both in our notes. Oh, I should talk about the notation. Okay. So the distance formula, like I said in the warm-up, you're just finding the distance between basically the x coordinates to find that one leg of the right triangle that you could draw, the difference of the y coordinates, and then you're finding the length of like that hypotenuse. Or pi theta. You could. Okay, here's the part that I should point out. The notation for magnitude is these double bars. They look similar to absolute value bars. And absolute value is distance away from 0. So it's like kind of similar. So if you see the double bars right here, double bars that are hugging that notation we talked about, like that vector PQ, that means magnitude. That means find the length. Okay, that's what that notation means. So obviously we can calculate that length, and then we can also calculate what direction the vector is going with the arrow by calculating like the slope of it. Okay, and that's another thing that we care about when we're talking about vectors is the direction, which can be found by either using like the slope formula. I always forget actually. 57. Take a week off and I forget what time our classes end and everything. Which Guzzi told us this one, y2 minus y1 over x2 minus x1, or you can do rise over run.
See, if you do Python, you just got the rise over run. You got one less thing.
Yeah.
See, so that's why you should do Python.
Okay, you can do that. That's right. Whatever you want to do. It's the same math. But, and actually drawing in like the horizontal and vertical components help us like in another type of form. It's called component form. So you like figure out what those are. So yeah, possibly. Okay. So if any of my directed line segments, so here's like kind of what they look like, not on a coordinate plane, but if they have the same magnitude, so they have the same length, and they're going the same direction, so they have the same slope from their initial point to their terminal point, then we say that these are all equivalent line segments, and that's what a vector is. It's the set of all the possible like equivalent directed line segments on a coordinate plane. We call that a vector. Okay, so here's like a nice little diagram for you. We can visually, I know you can't always like assume the length of these. We can visually see these all look like they're going the same direction, right? And have the same length. Yeah. If we wanted to be picky, we could get out and measure them, but we'll do an example problem in a second here. But here's what I would write in your notes: just equivalent directed line segments. And again, that means they have the same magnitude and same direction, and they're equivalent directed line segments represent a vector. A single vector is that. And then there's like just different forms that we can represent these. As I mentioned, I said like component form, something called linear combination. There's a third one. Directed line segment, yeah, and as a directed line segment, those are 3 ways basically. Okay, so let's try an example problem like this. Oh wait, no, there's one more notation thing quick, sorry. And then we'll try one. Okay, so here's basically what I just told you to write down, I guess, sorry. Right here. It says the set of all directed line segments that are equivalent is what a vector is. So here's the last notation thing. Another way we can notate vectors is they're often lowercase bolded letters. And they usually use letters such as U, V, and W. Okay? So anytime you see lowercase bold-faced letter, that's usually notating a vector. So if we took like that directed line segment, let's say PQ, we could have a lowercase bolded V, and that would notate our vector is that directed line segment PQ. Okay? So these mean the same thing. Initial point, terminal point. So just be on the lookout for like those lowercase letters, and that represents a vector like this. So they're calling like this directed line segment vector V. This vector U. Okay, so if you see those lowercase bolded, that's notating the vectors. And basically the vector is just all the possible like these line segments that all have the same magnitude and same direction. Okay. I think that's about it for that slide. It's just a lot of notation stuff, like I said. So let's try this example problem now. It says, show that u and v, so when they have that lowercase bolded, they're telling me vectors u and vector v. Show me that vector u and v are equivalent. So in order to be equivalent, they need to have the same magnitude, aka the same length, and they have to be going in the same direction. Now in this case, we can't just say, yeah, it looks like it. We have to like show it by finding their distances and finding their slopes.
So they have to be parallel.
Yes, they have to have the same slope. Yep. So, you gotta show they have the same magnitude, which is just the length. All right, so like I said, you can either do Pythag, make yourself a right triangle, seems like you guys like that, or use distance formula. Let's use the right notation for magnitude. The magnitude of the directed line segment PQ (2 squared plus 3 squared), 13, so that'd be the square root of 13. Oh, dude, should I show my work? Maybe. You get to that same spot if you do distance formula. Okay, there's the magnitude of PQ. And I'm okay with you guys just leaving it in numerical form. All right, magnitude of RS. The directed line segment RS. You can see here. Obviously, I'm going to get that same square root of 13. Okay, so they have the same magnitude. Check. Now we just have to make sure they are going the same direction. So to check that, we're just going to find the slope. Okay, I like Connor's idea here. We already have the rise over run, so just make sure you tack on like if it's going in the positive or negative direction with the plus or minus. I usually just kind of notate it this way, like the slope of the direct side line segment PQ would be 2/3 rise over run, or you can use the slope formula. What about the slope of RS? Same. All right, so that's all you have to do. If they ask you to show, or ask, are these vectors equivalent? You have to show same magnitude and same direction. It's not efficient. It's not sufficient. That's what I was saying. It's not sufficient just to do one or the other. Okay. Okay. So here's probably the most common form of writing and notating a vector. It's something called the component form. And it's basically you're just going to reposition whatever terminal and initial point they give you. We're just going to basically reposition the vector so that its initial point's at the origin. Because we know those are still considered like the same vector as long as they have the same magnitude and direction. So we're just going to take the directed line segment wherever it's located, and we're just going to relocate it here, and that's something called component form. It's kind of like, you know how we have like a bunch of different ways of writing an equation of a line. We have like standard form, slope-intercept form, point-slope form. Component form just allows us to do like a little bit more algebraic characteristic things to when it's written in like this component form. Just basically, like I said, another way to like represent a vector, probably the most common. Okay, so let's just kind of draw a picture here and follow along. So it says, let's have some initial point P1, P2, and the terminal points Q1, Q2. Let's just do it in quadrant 1 here. I kind of gave you a little blank space. You can tack numbers on if you want. Let's say P is 4, 2. I kind of tack numbers on here. So let's say this is my initial point, which they want me to call P1, P2, and then I'll write the actual numerical value, or the point 2, 4. And let's say that my terminal point, I'm going to do this actually. All right, I just said it. I don't know, how do you want to write it? Oh yeah, 4, 2. Oh my gosh, good catch. Shoo! 4, 2. After I just teased you guys about knowing how to plot points. All right, let's make our terminal point 10, 9. And this is just to give you like a visual of where this like little formula, if you will, this formula comes from by actually tacking on numbers here. So let's say Q, which they said is Q1, Q2. Here's my vector, initial point P to terminal point Q. And this would be the point 10, 9. Okay. So the component form of a vector uses almost like, I call them kind of like angled brackets, or they look like inequalities like this. So we have my vector PQ here. So it looks similar to an ordered pair, but it's not the same as an ordered pair. So they use these angled like brackets like so. And basically, the reason why it's called component form is we want to list the horizontal component of this vector and the vertical component. So how we find that is we basically just find like the difference between their x-coordinates. We find kind of like the distance, if you will, like the difference between these x-coordinates and the difference between these y-coordinates. So algebraically, if you were to look at this, if I want to find this distance, I would take Q1, whatever Q1 is, minus P1. Everybody see that? That would give me this distance right here, right? And if we were to do it with our numbers here, if I wanted to find that distance, I would do 10 minus 4, and that'd be 6, right? We'll do that in a second. And then that will be my horizontal component. Well, actually, let's look at the next one. And then to figure out the vertical component here, we would take our QT. QT. Q2. Sorry, I was thinking it's QT. No, not as fun. Minus my P2. And then you put that in an angled bracket again. Okay, so let's do it with the numbers and I'll kind of make a little bit more sense. So to find, let's call this, we'll keep PQ.
Yeah.
So to find this horizontal component of our vector, or the horizontal distance, we would take the 10 minus the 4, which would give us 6. So we all agree that distance is 6. We call that our horizontal component. The distance is between the x-coordinates 6. And then to find the vertical component, we would take the 9 minus the 2.
7.
Just 7, thank you. So 6, 7 is what we call component form of this vector. And we often label it then as V1, V2, where this first number right here, that's my horizontal component. Horizontal component. And then this right here is my vertical component. Okay, so let me show you one other thing. So basically, we just talked about how the vector is a set of all the same equivalent directed line segments. If I were to now plot the point 6, 7, and I know this is hard because we kind of just guesstimated some values here, 6, 7. The vector from the origin to that horizontal and vertical components should be an equivalent directed line segment. It should be like the same vector. Okay, so my drawing's not super to scale, but you can obviously see they're going in the same direction and they should be about the same length. So here's what you need to know. That's a little like proof, if you will, of like where this formula comes from to find it in component form. But when you see it, the number that's paired inside of those angled brackets that represents our initial point's always going to be at 0, 0, and our terminal point's always going to be at that number located inside, and that's going to be an equivalent vector.
Uh-oh.
Get there. That's when we're in this component form. This is, like I said, I feel like probably, linear combination form is also common. We won't get to that today by any means, but. All right, so then to find the magnitude of a vector in component form, same thing, distance formula or Precalc. So instead of like finding these distances, you can use the horizontal component, square that. Horizontal component squared, vertical component squared. That's really Precalc. Square root it, and you'll get the length of the vector. Does that make sense? Okay, that's basically just what a vector is. It lists that like horizontal and vertical components, and it's just a set of all those possible like directed line segments that have the same magnitude and same direction. All right, so let's just try an example here, and it's kind of a lot of vocab too. That's why I don't want to throw too many new forms at you today. Do you have a question?
Yeah, is it square root of 85?
Oh, this one? I didn't actually find it. Did you do 6 squared plus 7 squared?
Yeah.
So let's see, 36 and 49. 85? Yeah. Square root of 85. Okay, so let's try this one. It says find the component form and the magnitude of the vector that has the initial point 4, -7, and the terminal point -1, 5. So we can do this without even like graphing it. All right. So it says vector v, so lowercase bold letter. Okay, that's fine. They're writing it as a vector instead of a directed line segment, and you could do that too here if you want to. Like we could call this vector v if we want to. There's different ways we can like notate that, but vector v, and it has this initial point and this terminal point. So I'm basically trying to figure out, okay, what's the horizontal component between these two order pairs, and what's the vertical component. So the formula, if you will, is you always want to start with your terminal point, subtract off the initial point. That'll give you the horizontal component. And then same thing with their y coordinates, and that'll give you the vertical component, which we just saw visually why that works, right? So here I would do my terminal point -1 minus, and you do have to go in this order, 4. So my horizontal component of that vector is -5. And then to figure out the vertical component, terminal point 5 minus -7, aka you're just finding the distances between those. Maybe Precalc is better. You guys are selling me more and more that Precalc is a better way to go.
It is.
Multiple steps at once.
Yeah. Okay, so there's that vector in component form. So what that means, folks, if I were to draw like this vector, the initial point we just assume is at 0, 0. That's one of our characteristics with the component form. Initial point's always 0, 0. And then our terminal point would be at -5, 12. And so that directed line segment would be equivalent to this set of starting at 4, -7, and ending at -5. Okay, and have the same magnitude, same direction. All right, now they want us to find the magnitude. So we're just finding the length of that line segment. So again, we could just really use Precalc. Square root the horizontal component squared plus the vertical component squared. You're just adding up those two legs. Square root it to get the length of the hypotenuse. Oh, this comes out to a nice, perfect square. Yep, 13. Oh, this is a Pythagorean triple. We're learning those today in geometry. Good stuff. Okay. I feel like that's actually a pretty good stopping point.
Yeah,
I agree.
Because now we're going to get into vector operations and stuff. And
The only time I think Precalc would be bad is if your points aren't nice. Or decimals.
decimals are fractions. Yeah. But because like vectors are so like, I guess like notated with like those